tutorial class, right? So now we are on week 11. So week 11 will be covering the first part of the boundary layer theory, part 1, which will focus on the velocity profile within the boundary layer. Okay, and then next week Monday is a public holiday. All right, so take note that we will not have any online lecture on Monday. So it will be replaced on Tuesday. Instead of a lecture, it will be a guest lecture. All right, it's a guest lecture by Professor Salim from Swansea University. All right, so we will still follow our class time because Professor Salim, I think, is at UK or US, I can't remember. All right, so that's why this time is just nice for both us and Prof Salim. All right, so that will be Tuesday, and then on Thursday, take note, it will be our test. All right, Thursday, 2 to 4 p.m. So for anyone who missed the briefing last Tuesday, right, on a scope, I'll repeat it again later, and tomorrow I will do just a very quick and brief revision, all right, on some of the important points that you need to take note. All right, so that's the plan for week 12. All right, so then week 13, then we'll resume back on the topic about boundary layer theory. That's the part 2, which will focus on the thermal boundary layer. All right, we'll focus on the thermal boundary layer. And then on week 14, we will only have one class. That would be that will be our revision class. Okay, and since I think it would be better that it would be a physical class, right? So we will arrange it on Tuesday, right? Tuesday physical class. So only physical class is available. There will be no hybrid session. So you're informed 1 month in advance, right? So please make yourself available to attend this revision class. And this is a final class. So meaning on Monday we will not have any lecture class anymore on week 14. All right, no lecture class on Monday. So I've posted this all this in my times already. The information for each of the week from now onwards until week 14, so that you can refer to it. All right. So please make arrangement. All right. So if you're planning anything on week 14, okay. So make sure you attend the revision class. It's very important. All right. Now, so so any questions so far? Any questions so far? Okay, so I think your final exam paper for this module is quite late, right? Almost towards the end of the few days of the final exam season. So it's 9 or 5th, I can't remember, 9 or 5th August. All right. I'm lagging a bit. Others, is it really that I'm lagging a bit or lagging a lot? Oh my. Ah, okay. Then I try switch off my camera and see if it will be better or not. Usually, most probably it's a video. Is it better now? Is it better now? Okay, okay. Thanks for informing me early. Okay, let me confirm. It's okay now, is it? No. Oh my God. I switched my video now. Is it better? Everyone, could you please help to confirm? Is it okay now? Sounds similar. Let me see what I can do. Let's see. Is the voice that is slowed down, right? Okay, let me change.
Oh, okay. Is it okay now? Is it better now? I switch it to my iPad mic. Okay. Okay, yeah. So far, okay, yeah. All right. Because just now I'm using my laptop mic. I thought it's a new laptop provided by the university. It's supposed it should be fine. All right. Is it okay? May I just confirm one last time? If yes, then I'll begin because there are a lot of formulation today, a lot of derivation. Okay, thank you. All right. So, but luckily I write it out. So this is what will be going on for the next few weeks. All right. So just to do a quick repeat again in case if it's very choppy just now. So this week we'll cover boundary layer. All right. So we'll have our lecture and tutorial session, and tomorrow we will do a quick revision, right, for the test in case anyone missed the briefing on last Tuesday. All right. So week 12, take note. We will have no lecture class on Monday because it's public holiday, so it will replace with guest lecture 4 to 6 p.m. by Prof. Salin, and Thursday it will be our test 2 to 4 p.m. All right. So week 13, then we'll continue with the second part of the boundary layer theory, right, focusing on the thermal boundary layer. And week 14, we will only have revision class on Tuesday, and it will be a physical class, right? So there will be no hybrid session, all right? So, and that's our final class, okay? So please make sure you now save your calendar for this revision class, all right? So now, okay, all right. Now, so here is what we are going to cover this week. So how I'm going to organize our class this week is a bit different from what we do usually, where we go through the lecture, then only tutorial. For this week, I will combine lecture and tutorial together because the solution to the tutorial question is the same as what we are going to cover during lecture. So I don't want to speed up my speed to cover the lecture part, then repeat the same thing again during the tutorial. Right, so that's why I'll combine both later. When I go through the theory with you, I'll show you the question, and then we analyze the question together, and then we solve the solution. So you see, the solution is the same as what you see in the lecture slide. All right, but then when I go through in detail, then you may find it easier to understand. All right, so we will be introduced to the boundary layer theory for these week 11 and week 13. All right, so when we talk about boundary layer, there are actually three types of boundary layer because we have three types of transport phenomena, right? Which is the let me think. We have momentum transfer, heat transfer, and also heat and mass transfer. All right. So we have actually three types of transport phenomena, but the boundary layer that we are going to discuss will only cover about the velocity boundary layer and also the thermal boundary layer, which means this would be then for the momentum transfer, and this is for the heat transfer. All right, so we'll look at again, all right, the schematic diagram on the boundary layer thing. So focusing on the velocity boundary layer today, all right, so how the velocity, it varies, all right, from the surface of the plate to some distance far away from the plate. All right, and for this region here, all right, so we are going to look at, so what are some governing equations that we use to describe the velocity boundary layer? All right, and there are two methods that can be used to solve, all right, the velocity boundary layer, the velocity profile and the velocity boundary layer, which is the first one is we call it the exact solution. Right, so for this one, you are only going to learn how to simplify the governing equation. Right, you're only going to learn how to simplify the governing equation because the solution to it, right, you notice that it's actually a partial differential equation of the velocity to several independent variables. So we will not be able to solve it by hand, right? So the solution is actually is power series, right? It's a power series solution. All right, so we will only go look at the how to simplify it, and then how the final solution looks like. All right, the one that you learn how to solve it by hand, all right, so we call it the approximate solution method, all right, which is proposed by von Karman, or another name for it is the momentum integral method. All right, so for today, I will cover until this section here, how to simplify the governing equation if they are using the exact solution to solve it. All right, and then for tomorrow tutorial session, all right, so then we'll focus on this one, which is the momentum integral solution, right? So to solve the velocity boundary layer. All right, um, so to let you have an idea, so your final exam there are 6 questions, right? So all three learning outcomes will be tested. So this topic here, when we talk about the boundary layer, it will definitely be tested in final exam. All right. So there will definitely be one question that will be a question 6, which is about the boundary layer theory, either on velocity boundary layer theory or the thermal boundary layer theory. Okay, so please make sure you pay attention today, yeah, and tomorrow, and also during week 13. So don't miss your class. All right. So, okay. Now, so for the boundary layer theory topic, right, it's mapped to your third learning outcome, right? So for today, we are going to focus on the part for this week, all right? So we'll focus on the part of formulating the velocity profile for fluid flow, all right? So now, talking about boundary layer, what do you understand about the boundary layer? Why there is a boundary layer and what we are actually observing in the boundary layer? Would anyone like to give any opinion? What do you think? And why is it so important that you study about the boundary layer? Any guess? Anyone? Would anyone like to guess? You can put your opinion in the chat area. It's actually a very interesting topic if we ignore the formulation part. It's actually a very interesting topic. It explains quite a lot on why certain things are designed in certain geometry. All right, so now when we talk about the boundary layer, so you definitely always see something like this, right? You have a plate and you have a boundary layer which is drawn like this. So when we have the boundary layer, this section here drawn like this, it doesn't mean that the fluid only flow in this region. So what happens actually, all right, so you may have a very infinite a layer of fluid, right? A film of fluid which has infinite thickness. All right. So, but there would be a region. All right. There would be, for example, this one that I'm explaining. So let's say you have a fluid. All right. So it's at a velocity of v infinity, a uniform velocity of v infinity that flow over this plate here. All right. So when you flow over the plate, right? So at a region, this region here, which is beyond the boundary layer, so the one that I'm not highlighting in yellow, this region here, it will travels at a free stream velocity v infinity, right? But in the highlighted yellow color region, that's where you observe the change, right? So this whole region here highlighted in yellow, that's the velocity boundary layer, right? Where you observe that the velocity, it will varies from 0 to 0.99 of the free stream velocity, all right? And this would, so as this whole region here is where you will observe this change in the velocity. All right. So now this is an example. If you have a fluid that flow past a flat plate, right, and we have velocity boundary layer and variation of velocity within this region. One thing is because of the viscosity of the fluid, right? The viscosity of the fluid, it will contribute. Okay, the viscosity of fluid is it will contribute to the resistance of flow and also the friction, right? The friction between the fluid layers and also the friction between the fluid and also the surface, or you can say also as the shear stress, right? So and the momentum flux is also equivalent to the shear stress, right? For what we have been discussing so far, right? So these are all the reasons that contributes to the presence of the velocity boundary layer. Now, how it actually affects a lot of things and how things work, right? So one of it, all right, so if you look at here, let's say we have a sphere, right, a spherical ball of a very, let's say you imagine this as a ball, all right, with a very smooth surface, all right, a smooth surface, all right. So what happens when the fluid, so when we talk about fluid, it could be gas, it could be liquid, all right. So when the fluid, it flow towards this smooth ball here, right? What happens when it first, right, the fluid flow up to this point here? There's a point here which we call it the stagnation point, right? So this point here, the stagnation point, and it's at this point here the velocity will almost come to a zero, a value of zero, right? So when the fluid flow up to this point, and then the fluid, it will then start to divert, right? It will divert and then it will start to flow past the ball and then into towards the back of the ball. Now, what happens here? So, within this region, right? Within this region here, then the velocity boundary layer starts to develop. All right, the velocity boundary layer, it starts to develop. All right, and and you notice that the stream, right? So it's being separated towards the rear part of this ball, right? And then it will create what we call it, this section here, the wake, wick area, right? The wick area where you have eddies, right, and the mixing of the fluid. And actually, what happens here then, it will create a low pressure region, right? So it will create a low pressure region where at the front here we have the high pressure region, right? The high pressure region. So which means um, between the front and the front and the behind part of the ball, right, you have a very big difference in pressure gradient, right? And this then will actually create what they call it the drag force, right? The drag force that is a force that oppose what is happening to the motion of the ball. So the ball is let's say if it's moving towards the front, but when the fluid impact on it, all right, so with the drag force, so it will affect the speed of the ball that is traveling. So this boundary layer, the existence of this boundary layer, then it will then affect the overall speed, the average speed of the ball. If you have a very great pressure difference between the front and the behind part of the ball, right, because of the drag force. Okay, so then if we want to speed up something, all right, so that also explains why the wings, right, of airplane, all right, so and some submarine, they are designed in this kind of manner, this geometry here, the streamline manner here, because with this geometry then, so you'll notice that, so when the fluid, right, flow past this streamline object, right, so it will then be the boundary layer or the fluid, it will actually be diverted smoothly, right, towards the end part of the body, right? So it's not separated. The fluid is not separated far apart, where you just have a very, right, a very small weak area. So which mean, right? So the pressure here at the front and the back of the streamline object, right? They might be very small pressure difference only, and then it will help to minimize the drag force as well. And therefore, right, so and even if you look at, if you, let's say we analyze, all right, so we analyze the velocity boundary layer, all right, so for streamer object, you notice that its thickness, it will be even smaller, it's very thin, right? So as if the fluid is actually stick on the object when it's traveling, so you have a more smooth, right, boundary layer, right? So that helps to maintain the speed of the object. Okay, so if you are interested on the detail and look at, like, so actually, all right, so if it's at this angle here, when the streamline object is at this angle, all right, so the speed is still quite okay. But let's say you just imagine, right, if we tilt it, right, so if we tilt it, that is very extreme then. All right, so when the fluid flow past here, right, okay, it will be directed here, but on the top part, right, so notice that it will then form like this. So there will be the wick area here, right? So when the angle is being changed, right, it's tilted. So again, this will create the low pressure region. And it's actually this concept here, the velocity boundary layer concept, that actually affect, right, or it's the one that they use those marines or the space or anything deal with aerospace, they use to control, right? So how the plane can lift up, right, by changing the flap, right, the position of the flap on the wings, right, that they will distort the boundary layer shape, right, to control the lifting or when the plane is landing, right? So if you'd like to know further, right, so you can Google more, all right? Okay, so now this is another example here. If you have a ship that sail through the seas, right? So you notice that most of the time, when you watch any movie, right, there's a white color wave that form around the body of the ship. So that's actually the velocity boundary layer, and this section here is where all the wake that will occurs, or the drag force, right, that occurs. Okay. Now, so when we talk about the velocity boundary layer, right? Okay, so the fluid motion is also greatly affected by the solid surface, not only by the fluid itself, that it has certain viscosity resistant to fluid flow, but the surface, right, whether it's smooth, whether it's rough, all right, it will also affect the velocity boundary layer. So we'll look at this one, the effect, in the next slide. All right, so how they use it to control the speed of certain object. So it's not to say that a smooth surface is bad, or a rough surface is better or bad also. It depends from cases, right? It depends on the application. All right. So for certain times, a rough surface, it might cause very severe problem, or certain times the rough surface is actually preferred for certain application. Now what happens during velocity boundary layer? Let's say if we have a fluid flow over the plate, right? So this is the region that you observe the change of the velocity from 0 to 0.99 of the v infinity. So the region beyond this velocity boundary layer here, the region beyond the velocity boundary layer is the region where the fluid, it has zero viscosity, right? So it's traveling at a free stream velocity, and your viscosity is very important in this velocity boundary layer here, but it's not significant, right? It's not significant uh, when it's not away from the velocity boundary layer. All right. So, and this boundary layer here, the velocity boundary layer, is actually very, very, very thin. From what I've found, like they mentioned, it's around only like 0.2 to around 200 micrometer. All right, so we can then derive some simple solution. All right, so to obtain an expression to describe how the velocity change within the velocity boundary layer, or to estimate the thickness of the velocity boundary layer. All right, so some solution has already been proposed by Prandtl, and also we have also one common that we are going to cover next tomorrow. And today we are going to look at the Blassius solution, right, to this governing equation for the velocity boundary layer. Now, before we look at the application part, okay, so let's go through quickly on the theoretical part, right? So we have covered some of the concept when we formulate the velocity profile for different geometries previously, either using the Shell momentum balance method or the Navier-Stokes equation method, right? But now we are looking at the boundary layer itself. So what's the difference from what we are discussing today and all those previous is when we look at the velocity boundary layer, what happens, right? So let's say if we have the flow past a plate, all right? So then a boundary layer will form, right? Because of the friction between the fluid and also the surface, or the resistance to fluid flow by the fluid itself as well, right? So when the fluid flowing, right, it will flow at a uniform velocity v infinity, right? So then within the velocity boundary layer here, so what happens? Okay, so I'll draw it first, right? So let's say this is the x direction, this is the y direction. So the fluid is flowing in an x direction. So at the region, so let's say which is just at the surface, the velocity of this fluid here, it will be zero, right? So that's what we know the no slip condition. Okay, no slip condition. But at some position y, which is sufficiently far away, right, from the surface, so I'm not writing it as delta as the delta anymore, right? Because it depends uh, on on the position, right? So because if you look at it, right, so when we talk about the velocity boundary layer, this section here, the thickness, right? So let's say this one, right? So the thickness, all right? So you notice that the thickness, right? The thickness of the velocity boundary layer, it actually changed, right? It actually changed with the position x. It's getting thicker, thicker, and thicker, right? Which eventually it penetrates deeper into the infinite, the film of fluid with infinite thickness, right? So in this case, this is one of the difference, right? So from what we have been discussing previously, because previously most of the time, right, in let's say the y direction, we know what is the definite value for it. But when it comes to the velocity boundary layer, the thickness of the velocity boundary layer it actually increase in x direction. So which means delta is a function of x. All right. So then, at the distance sufficiently far away, right, from the surface, your velocity, the velocity at this edge here, right, the edge of the velocity profile, it will approach v infinity. Okay, it will approach v infinity. Okay, so that's a quick recap back on the velocity boundary layer part. All right, so it's actually the same thing. Just to inform you on some of the terms like this, we call it the leading edge. All right, so the region where your viscosity here is not significant anymore, right? So that's what we call also the potential flow region. right? So, and whenever we talk about the boundary layer region, then it's the region where the velocity, it varies from 0 to 0.99 of the free stream velocity. Okay, so uh, okay, yeah, sometimes, right, it could be also the case, like what happens to the streamline body, right? So it may happen where in this region here, the very thin boundary layer that forms over the surface, right, of the streamline object. So the boundary layer, it may looks like this. It will be some case like, so at the start, it may be the fluid may flow in a streamlined manner in the boundary layer, and then maybe towards some further away from the front part of an object, the fluid, it may start to transition, right? It may start to transit. There will be transition to turbulent flow as well, right? So, and for information, the boundary layer, right? We have two types as well, right? So we have laminar boundary layer and turbulent boundary layer. But our formulation will focus on just the laminar boundary layer. Okay, so we'll focus only on the laminar boundary layer. So if it's a turbulent boundary layer, so you can actually expect the delta x, right, the thickness of the if it's a turbulent velocity boundary layer, all right, so velocity boundary layer, its thickness would be smaller as compared to that for the laminar, right, laminar velocity boundary layer, its thickness would be larger. Okay, so and that's why when if we could, right, so modify the boundary layer around the object into a turbulent flow, right, for certain cases, then it can help to improve the velocity, the average velocity of that object. And this okay, the application is in next few more slides. Okay, so I'll talk about this later. Okay, and I'll show you a very interesting video as well. So now for the Reynolds number, then how do we know whether the boundary layer, the fluid, when it flows in the boundary layer here, whether it's in laminar or in turbulent flow, right? So then it's given by this range here. So if it's laminar flow, then the Reynolds number. So for calculation of Reynolds number, you can see here, right? So it's kind of similar for the case when you have flow past a plate, right? So where last time you calculate as rho VL per mu. So this one, and they express it in terms of x. What is the linear dimension in the x direction for that object? Okay, so it's still density. Then you should calculate using the free stream velocity. Okay, the free stream velocity, multiplied to what is the linear dimension of the object and the viscosity of the fluid. All right, so with this, so if it's less than 210 to the power of 5, then it's a laminar flow. And then for turbulent flow, it should be greater than 10 to the power of 6. So anything between these two values, then which means the fluid within the velocity boundary layer is traveling at it would be traveling in the transition manner. All right, so now if you would like to know more about the boundary layer part, to look at how it changed, right? So you can take some time to explore this video here. I think it's something that deals with they are testing, right? So for streamline object, so how the velocity boundary layer looks like, right, when it's not tilted or when it's tilted to a certain angle, so that you can see, right? So there will be a lot of wake area here that actually created a very high drag force that affect the speed of that object. All right, so now, so then here comes the part why boundary layer theory or why boundary layer is very important, right? So especially for those who are going to work on something that is related to fluid dynamics, like even in designing the race car, right? So it's also affected by this theory here, the racing car, uh, the shape of the wings of the plane, and even and sometimes not only in those aerospace or the marine industry, but also let's say for the food industry or those who are manufacturing things using the extrusion. So this is an example of an extrusion process. Let's say they use extruder to produce some, for example, to form the metal into different shape here, such as whether it will come out as a tube, whether as a flat sheet, or certain structure, right? So all this is affected by the boundary layer theory. So usually what happens is those matter, it will be first melted right, then it will go through the extruder here. So then by controlling the speed of the extruder to a certain extent, right, so we will be able to come up with those metal in different shape. And for information like those like some of the, if we are talking about food, the like twister, right, so it's actually come through the extrusion process. It's extrusion process. Okay, now then whether uh, whether the for the velocity boundary layer, right, so would it would a smooth surface or a rough surface would be more preferred, right? So as mentioned, it actually depends on case to case. So let's say when we talk about some example in sports science, right? So why is the golf ball being designed in a way that there's so many dimples, right? It's not the reason for such that it will help us to hold it better. That's not the reason. All right. So if you understand the velocity boundary layer, so let's say for a very smooth surface ball, right? So what happens then? You notice that the boundary layer, right? So when the fluid flow, it will then be separated, and then there will be it will creating large area of wick here. So you have difference of pressure, right? You have a higher pressure at the front of the ball, and at the rear part of the ball, you have a lower pressure region. So the large pressure gradient, it will then create a very large drag force. All right, which then this will then slow down the velocity of the overall velocity or the average velocity of this object. So with this dimple, right, created on the surface of the golf ball, right, so they call it as an artificial turbulator generator. So it will create those like mixing, right? So you then the rough surface on the ball, right? So you then create mixing. So because it will then interrupt the laminar flow of the fluid, right? So then the fluid will flows in eddies, and it's such that is mixing. So when you have mixing, if you recall back, right? So when you have mixing, which means then the momentum it will transfer closer towards the surface, right? So in this way, then the velocity, all right, so it will actually be more uniform, right, within the region where you have turbulence. So in this way, right, so it will help the fluid as if it will stick to the ball, and then your fluid, right, it will divert it to uh, the further down or deeper into the rear part of the ball, so that this region here, the wick region, right, the total area of it, it will be reduced further, and then it will then reduce also the pressure gradient between the front and the rear part of the ball. So then it also helps to lower the drag force, right, that actually oppose the motion of the object, and then it helps to increase the overall velocity. All right, so this is an example where, let's say, a rough surface is actually preferred, right? Rough surface is preferred. But there would be some case, right? So, like last time, what happens to NASA space shuttle? The rough surface actually create a very serious problem. All right. So, okay, give me some time to do the setup so that I can show you this video here. Just a quick one. Okay. Let me change my device for a while. Okay. Ah, okay. Hold on. So it's actually a very interesting video. Okay. Okay. So, all right. I hope you can see this screen now. Right. So let's have a look what happens. Right. So in this case that has a rough surface that actually create a very serious problem.
In 2005, NASA launched the Space Shuttle Discovery on STS-114, the first mission since the loss of Columbia and her crew. For safety, NASA instituted new procedures to inspect the space shuttle in orbit. One of the new procedures was a pitch maneuver prior to docking with the International Space Station. This allowed astronauts on board the station to take photos of Discovery's heat shield so that engineers on the ground could inspect it for damage. It was one of these high-resolution photos that turned up a couple of small details with the potential to become a big problem. Engineers found that 2 gap fillers were sticking out near the front of the space shuttle. Gap fillers are small, ceramic-reinforced bits of fabric that are tucked between the heat shield tiles, although the gap fillers were only sticking out about 25 millimeters, or the diameter of a US quarter. Even roughness that small might be a problem during re-entry. Exactly why that's the case is a question of boundary layer stability and the transition from laminar to turbulent flow. Joining me today to help explain is Diana Cowan of Physics Girl. Hey, Diana.
Hi, Nicole. Thanks for having me.
Thanks for joining me. So stability is a concept that shows up a lot in physics. How do you usually think of it?
I usually think of stability as whether something's in equilibrium. So, for example, a ball that's sitting on the top of a hill is in an unstable equilibrium, meaning that if you give it a little nudge, it'll just roll off the hill. If it's in a bowl or a valley, it's in a stable equilibrium. So if you give it a little nudge, it'll roll up a little bit, but it'll come right back down to its position. So that's an everyday example of stability in physics. But what does stability look like for you? How does it relate to fluid dynamics and the space shuttle?
That's a really great question. So in aerodynamics, a lot of the time we don't talk about what's stable or unstable. We talk about whether flow is laminar or turbulent. The laminar flow is smooth and orderly. It's like when you first turn on a water faucet and it's all nice and clear. Turbulent flow is like what you get when you turn the water faucet on all the way and it gets crazy and disordered and kind of random. Flow near an object right at the surface is an area that we call the boundary layer, and that boundary layer can be either laminar or turbulent. Typically, a boundary layer will start out laminar, and if it's disturbed, it'll become turbulent. Disturbances that enter the boundary layer start out so tiny that they're impossible to see or measure. But if the boundary layer is unstable to those disturbances, then they'll grow as they move downstream, eventually becoming large enough to alter the flow. When the disturbances get big enough, they cause the boundary layer to become turbulent.
So if a boundary layer is stable to a disturbance, then it's kind of like the ball sitting in the valley, where if it's disturbed, it'll roll back down and the flow will stay laminar. Whereas if it's unstable to a disturbance, then it's more like the ball sitting on the top of the hill and it'll roll down when disturbed and the flow will become turbulent.
Yep.
Okay, I got it. So is it a problem when a flow becomes turbulent?
It depends on the situation. So generally speaking, a laminar boundary layer has less friction-based drag than a turbulent one does.
So a flow that's laminar over a surface, for example, an airplane wing, has less friction-based drag. So an airplane can go further on the same amount of fuel.
Exactly. Sometimes, though, turbulence is helpful. Like when you're pouring milk in your coffee, if there weren't turbulence, you would have to wait several days for the milk to distribute through the coffee.
So turbulent flow is useful in some situations, but typically not in air travel.
Yes. And that brings us back to the space shuttle.
I think I see where you're going here. So the gap fillers that were sticking out could potentially cause turbulent flow.
Yeah. Boundary layers can be unstable to all kinds of disturbances, including surface roughness. Relative to the size of the space shuttle, the roughness from the gap fillers was not very large. If we scaled it to the size of this Lego space shuttle, that roughness would be roughly the size of the width of a human hair. The physics of how roughness affects boundary layers, especially at the really high speeds that the space shuttle sees during re-entry, is complicated and it's not very well understood.
I see. So even with simulations, the engineers on the ground were worried that these itty-bitty gap fillers might potentially cause a serious problem on re-entry.
Exactly. So the problem is that the gap fillers were located up here near the nose and the landing gear. So that means that if transition did happen, you would have turbulent flow over most of the underside of the space shuttle. The space shuttle was built to withstand the highest temperatures on the nose and along the leading edges of its wing. They used special material there, reinforced carbon-carbon, that was good to above 2,000 degrees Celsius. The rest of the space shuttle was covered in heat tiles that were only good to about 1,200 degrees Celsius. A turbulent boundary layer on the underside of the vehicle means that it would see substantially higher temperatures than normal. That same turbulence that's so great at mixing your coffee is going to be pulling plasma that's more than 3,000 degrees Celsius closer to the underside of the space shuttle.
That is incredibly hot.
Yeah, it's a pretty serious problem.
What did NASA do? What did they do about the gap fillers?
So NASA did a spacewalk to the underside of the space shuttle, which was something they'd never done before. They sent astronaut Steve Robinson down to the bottom of the space shuttle and had him pull out the gap fillers by hand.
Whoa.
The shuttle landed safely, and NASA launched new research programs into the effects of surface roughness on boundary layer transition. That's actually part of what funded my PhD research. So thanks for watching, and special thanks to Diana for joining me today.
Thanks for having me.
If you'd like to see a more down-to-earth application for roughness and boundary layer transition, you should check out Diana's latest video.
You'll learn about the reverse Magnus effect and how surface roughness affects.
Okay, so that's how important the boundary layer is. Now, okay, let me change back, because what happens just now is, even for the gap filler, there are only few right? So you can see how it actually will disturbs the turbulent, right? Disturb the shape of the boundary layer, and then when there's very high speed, right? When the boundary layer is changed from laminar to turbulent, right? So then it would create a very high speed, and you just imagine when it's re-entry back to Earth, right? The friction between the thing, right? The space shuttle and the atmospheric air, right? So it would create then the friction. It would then cause a very very high temperature, and then with the material that for that part is not heat resistant, right? So it will actually burn then. All right. So the next part it will be on a more theoretical part on all those derivation really. So I think maybe before we proceed to that part, right? So any question at the moment, right? So any question at the moment so far, everyone? If not, then we'll just take a short break for around 3 minutes, right, before we continue to look at the theoretical part. No questions so far? If so, then let's come back at 10:50, right? Come back at 10:50, then we will proceed with this one here, right? How to simplify the Gaussian equation for the boundary layer. Okay, right? So come back at 10:50 a.m. Okay, it's 10:50 already. So hopefully everyone is back up. Okay, so we will continue with the lecture part. Now, so just now for the video just now, right, and what we see here, the example here, so you can see the difference, right? How sometimes the rough surface is actually being preferred, while this one here for the space shuttle, the rough surface is not preferred at all, right? So that's why it depends on case to case. All right. So then, as for the racing car, definitely so you can look further into it how actually the boundary layer actually affect also the design of the shape of the racing car. Okay, so I think all right, so if you have time or if you're really interested, I have actually posted something on week 8 as well about this one, how why you need to learn about the boundary layer, why you are learning about the velocity profile, and then why you are learning all those Navier-Stokes equation. All these they actually apply it in the racing car industry when they want to like further improve the design of the racing car, right? So, and how to simulate it. I think it's a video that is being recorded by the Honda. Is it Honda? I don't remember. So for that, all right. So you can look at those extra materials, right? So that I share with you in week 8. I think there's one video and 2 articles, right? So you can take some time to look at it. And then next week on Tuesday, right, then Prof. Salim will then share with you more about his experience for his research in analyzing all this velocity profile thing, how it applies to improve some of the things around the university, at his university, and some of the project, all right, the industry project. Okay, so that will be next week. All right. So now we will look at the theoretical part. All right. So okay, we are going to look at what are the governing equations that are going to involve. So there are actually two, right? So one is the equation of continuity, and then another one which is quite similar to the Navier-Stokes equation, right? It's the equation of change of the momentum, right? That with the complete one, all right? Previously when we worked with the Navier-Stokes equation or the Shelburne balanced momentum method, right? So we are making assumption that certain terms is negligible, right? Then we will assume it to be 0 so that we can simplify it. So for today, you are going to learn how theoretically and systematically we can really know that that value would be close to 0, right? So that will be what we are going to cover for the first part today. And that method, we call it the what's the name already? Oh my, let me see. What's the name? Suddenly, I couldn't remember. The order of magnitude. Okay. Bring the order of magnitude. All right. So the method that we are going to use to simplify it, we call it the order of magnitude. That you apply, and from there, we can actually estimate how close the value is to 0, and from there, what's the reason? From there, then that's the reason that we can use to justify that we can assume that term to be 0. Okay, so that's the first part. Then after this, we will look at the exact solution method that is proposed by Blasius on how he further simplified the governing equation, right? He proposed method to simplify the governing equation. Okay, we'll look at how to simplify it only, but we are not going to solve it, right? Because it's still very complicated, right? So to solve it, then we'll need to learn tomorrow the approximate solution method. All right, so we'll only cover these 2 parts today. All right, so now let's look at the first part here. All right, so what are the 2 governing equations for the boundary layer? All right, so the first one is the equation of change. Right, this is the equation of continuity. Yeah, the continuity equation, which means it's related to the mass balance equation. And we are only considering 2-dimensional flow, right? So for the velocity in x direction, so just now for the case, so we are discussing based on the case now where you have a fluid flow over a flat plate, all right? So we are observing what is it changed in velocity in the x direction and also the y direction. So we are assuming, right? So the width of this film here is of infinite width, right? So and then we are assuming that the vz is equals to 0. All right, so then we'll also need to apply the Navier-Stokes equation, right? So for this 2-dimensional flow here, but if you look at this Navier-Stokes equation, right, you'll notice that the term here, there's one term here which is related to velocity in the z direction, right? Which we have already dropped it here, assuming that there's no velocity change in the z direction. And there's another thing here which is the body force, right, which is related to density multiplied to the gravitational force. This one is also assumed to be 0 for this case here because of the horizontal flow, right? So we will work starting from these 3 equations here. All right, so now when let's say, right, if we have a steady 2-dimensional flow of fluid with a constant density and viscosity around this submerged object here. Now, because the velocity boundary layer, right, or the boundary layer itself is a very, very thin layer from 0.2 to around 200 micrometer. So it's so thin that although this submerged object, right, as if there is some curve, but it's so thin that you can actually assume that this actually happens over a flat plate. All right, so the curvature effect is no longer important, right? Unless it's really that you have a very high pressure gradient at the front of the object, or a very low pressure gradient at the rear of the object. So when you have a very big pressure gradient, then the curvature effect you need to take into consideration, and which means the pressure gradient you have to take into consideration as well. But let's say for this case here, all right, so let's say we assume that the pressure gradient, they didn't assume it yet, all right. So for this example, when we look at how to check the boundary layer, right, so using an order of magnitude method to simplify it, all right, so we are still not assuming anything about the pressure gradient yet, all right. So but what happens here, they are assuming that the velocity profile is, although, right, so for most of the case that we discussed last time, right, when we draw a velocity profile, it has some curve, right? So for showing this one, so assuming that it's a very, very thin boundary layer, so they're assuming that this gradient, the gradient of the velocity boundary layer here is almost like just a linear curve. So which means instead of the curvature, right, so because of the very thin boundary layer, they are assuming that the boundary layer, it has a gradient of almost a linear curve. All right, so the curve effect is no longer important, and the change in velocity with distance, all right, so it's assumed to be almost linear for its gradient. All right, so then now I have also uploaded, if you check my times, right, so there are 3 reference material. Okay, so you can download it, because the solution in your slide is being separated into several slides. It might be a bit inconvenient for some of you to refer it, so that's why I also uploaded the PDF version, right, so that it's a continuous one, right, so you can download it for your revision later then, right, so that it's more convenient for you to do the revision. All right, so now then we will try to now use the order of magnitude method, right, the order of magnitude method, right? So to prove how we can first simplify this governing equation first, all right? So now, so for okay, how to simplify the governing equation? So about this order of magnitude method is like you're comparing a parameter to a reference value, right? So from there, then you can estimate whether the fraction of that parameter is it very, very small, so small that such that it's close to 0, that you can assume its effect to be negligible, and then that's why we can opt it out from our analysis. Okay, so it is like a yardstick. So for this case then, so what is the yardstick that we use for, or the reference, right, that we use for the comparison? So for flow, right, because this is in x direction, this is in y direction, right? So in x direction, so let's say the linear dimension of the plate is L0, right? So it's denoted by the L0. So it's very, very long, right? So the linear dimension of the submerged object. So this is one of the reference parameter. And then another one, it would be the thickness, right? So let's say we denote it by the delta naught. The boundary layer thickness is one of it. And the third one is, so we know that, right? So within the boundary layer, the velocity, it varies from 0 to 0.99 of V infinity, right? And V infinity would then be the maximum magnitude of the velocity then. So the third yardstick, it would then the V infinity. Okay, so by setting these 3 then as a reference parameter, then we can compare whether a term can be assumed to be negligible. Okay, so now let's say, let me see. Okay, let's say we start with the first one, the one of the term which is in the Navier-Stokes equation, dvx dy, this one. All right, so now for dvx, partial derivative for velocity in x direction with respect to y direction, right? So how we do it? So you express it as the order of magnitude. So for velocity in x direction, right? So we know that it varies from 0 to v infinity, and v infinity is the maximum one. So we'll put v infinity here. While in the y direction, the maximum magnitude in the y direction, right? So here in the y direction, then is delta naught, right? So it will then be delta naught. So this is how you can express it. And it's with this one here, then you notice that it's actually a linear, right? It's a linear value, and that's why when they are trying to solve this using the order of magnitude, simplifying the boundary layer theory, right? So they are assuming that the velocity profile here, it has like a linear gradient instead of this the curved one. Okay. Now, then that's for first derivative of Vx respect to y, right? So then we'll try to write also for the first partial derivative of Vx respect to x. So again, velocity in x direction, maximum magnitude is V infinity, while in x direction, the maximum magnitude then is the linear dimension of the plate. So it's V infinity divided by L naught. All right. So, but with this ratio here, we are still we are not sure, right, whether it's sufficiently small or not, because this is divided by delta naught. Most probably is quite large, right? So that's why this term here will not remove it yet, right? So this V infinity divided by L naught, but same thing, right? So we do not know this V infinity is how large of the V infinity yet. So unless the ratio is something like delta naught divided by L naught, so you know that, right? So velocity boundary layer, the thickness of it, in some, the common range is around 0.2 to 200 micrometer, right? So which means this is a very, very, very small value, right? And if the dimension, the linear dimension of the object is very large, which means this is a very large value, right? So then the ratio of this, it would be, most probably, it would be almost close to zero. So if later, when we apply the order of magnitude method to analyze each of this term here, and it carries some ratio of, let's say, delta naught divided by L naught, or delta naught divided by L naught to the power of 2 or 3, then you know that term, it would be very, very small, so small that it goes to zero. So which means then we can remove it from the boundary layer equation, this one here. Okay, now, so just now we have done for first partial derivative of Vx respect to y, and the one which is respect to x already, right? So now let's check also for other term. Okay, so let's say this one here. All right, so knowing that from the continuity equation, right, partial derivative of Vx respect to x is plus partial derivative of Vy respect to y is equal to 0. So if we rearrange it, right, then dvx dx, it will then be equals to negative for partial derivative of Vy respect to y, right? So which means the order of magnitude for this term here, it should be the same as this term. So now when we are comparing the order of magnitude, the negative effect is not important, because we want to know how big or how small is the value only. All right, so since it's dvx dx is equal to negative of dvy vy, right? So then for partial derivative of Vy respect to y, for its order magnitude, it should be the same as this one. So let's check. So just now we have found that it's actually from of the magnitude of V infinity divided by L naught. Okay, so that's the magnitude of this term here. All right, so then we'll proceed further to try to get an expression for Vy. Right, so if partial derivative of Vy respect to y, the order magnitude is V infinity divided by L naught. Okay, and if we want to get the order of magnitude for Vy, so what we'll do is we'll integrate. So we'll integrate this term here respect to y, right? So integrating it, so for integration, it's like you are multiplying this order of magnitude here that exists is at the existing one, all right, in partial derivative form with the maximum magnitude with respect to the y then, right? So that's why you can see it's expressed as so y here, right? So we know that the maximum magnitude in the y direction is delta naught, right? So that's why it's delta naught divided by L naught, then multiplied to V infinity. Okay, it is just this simple here, right? So that's why, right? So if you recall back, when we have flow over a flat plate, right? So most of the time, when the fluid is flowing in x direction, your Vx, right? So we'll definitely retain it. And we are assuming the variation of velocity in the y, this one, the Vy, right? So velocity in the y direction, right? So it will be zero because of this. So this is now the very systematic and theoretical approach in proving, right? So why Vy is equals to zero, right? So here, because you can see now, it's delta naught divided by L naught. It's quite a small value. It definitely is a value that is much, much, much smaller than 1. Okay, so now, and this also shows that, right? So if you compare, so because your Vx, the maximum magnitude is V infinity, right? So this also help us to prove that your Vy is sufficiently smaller than Vx, okay, for the comparison. All right, now then we continue further. We try to get the expression for partial derivative of Vy respect to x. All right, so then now when we want to when you integrate, it's as if you are multiplying, right? You're multiplying the maximum magnitude for that parameters. So when we are going to take partial derivative of this one, right, of the Vy respect to x, then it's as if you're doing the division, right? So the division for the maximum magnitude in respect to x. So which means then it will be delta naught, all right, and then divided by L naught square, right? So to divide this term further by L naught, that's the L naught is the maximum magnitude for the x direction, right? So then multiply back to the V infinity. So with this, you also notice that this is a very, 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 very small fraction as well, right? It's also a very small fraction. Okay, so now, um, okay, I'll then just do a quick one for this one here. All right, so so that you can have a look how they actually get all these terms here. So now Vx, the maximum magnitude is V infinity, right? So dVx dx. So let's check dVx dx, which is here is delta, this one, Vx is V infinity over L naught. All right, so that's why V infinity over L naught. So when you combine it, that's why you get order of magnitude of V infinity square over L naught. Right, so you do the same to the rest. So for Vy, right, so let's see here, Vy here, okay, this is the answer, delta over L naught. So okay, so maybe, okay, let me write here. So it's for the order of delta over L naught multiplied to V infinity, and as for dVx dy, then it's V infinity divided by delta naught, right? So then you simplify this, suppose then the order of magnitude, it would then be V infinity square divided by L naught, all right? So if you look at here, if you compare these two, right, these two here, right, is of the same order of magnitude, right? And these two terms here is actually, let's see where is this two term, is actually for this one and this one. So usually, right, because for let's say the homogeneity in the unit or for the equation, right? So the one that is on the same side, so they have both here the same magnitude, right? The order of magnitude is V infinity square over L naught. All right. So now then we look at these two terms here, these two last term here. So partial derivative of Vx respect to x. So now what happens earlier? So the first partial derivative of Vx respect to x is from, it will varies from V infinity to L naught, right? And then when it's the second partial derivative, which means you will divide it further with L naught. So that's why the order of magnitude is V infinity over L naught square. Okay. Then the next one, the second derivative of Vx respect to y. So if I'm going to write the first derivative of Vx respect to y, the order of magnitude will be V infinity to delta naught, right? And then we differentiate for one more time, so then it will be divided by 1 over delta naught. So that's why the order of magnitude for this term here, it will be V infinity divided by delta naught square. All right, so these are all the magnitude for the first equation here, right? So for the, this one is the Navier-Stokes equation, right? For flow in x direction, right? This is for flow in x direction. So next we are going to look at, how about this one? This one is the one that we usually assume it to be negligible, right? Okay, and before this, before this, now if you compare these two terms here, let's compare these two terms here. All right, okay, for these two. Okay, So for the second partial derivative of Vx respect to x, this term, if you recall back previously when we do an Navier-Stokes equation for flow in x direction, most of the time we assume this term here to be negligible, right? Because we know that your velocity in x direction, it will varies in the y direction. And definitely the second derivative of Vx respect to z, we also assume it to be 0. So why this, and last time, this term here, so because this one, second derivative of Vx respect to z, you assume it to be 0 where you prove it from the equation of continuity, right? But this term here, last time we couldn't justify it clearly, right? You might still have some doubt why this is 0 when we only justify it based on that velocity only varies in y direction. Now here is the proof then, all right? So if you compare, right, so you notice from second derivative of Vx respect to x, its magnitude is V infinity divided by L naught square. This is L naught square. So very L naught, let's say the linear dimension is a very large one. And if you compare it to second derivative of Vx respect to y, right? So the order of magnitude is V infinity divided by delta naught square. It's a smaller fraction then, right? So from here, then you'll notice that the second derivative of Vx respect to x, right, is much more smaller. The magnitude of it is much more smaller than second derivative of Vx respect to y. All right, so that's the theoretical proof for it, why we assume it to be negligible. Okay, now the rest here for the equation 2, right? So if you all want, I think I'll need to reserve some time to discuss the next part with you all. So if you have time, right, so you can try it out as well for this section here, how to get the order of magnitude for this field. Now, I'll just quickly, right, so we do a quick comparison. So if you notice here, right, so for the left hand side, right, so for the left hand side of the second equation, this term and this term, which is referring to this two, so the order of magnitude, right, is delta naught divided by L naught square. So if you know that delta naught divided by L naught is a value that is much smaller than 1, right, so which means this would be a value that is even much smaller than this fraction here, right? So that's why, right, so for the second equation here, for flow in y direction, right, for the Navier-Stokes equation, that's why here we can assume it to be negligible. All right, so same goes with this one. So if you look at the order of magnitude, so that's why this term goes to 0. And what's some more here for this term here, the second derivative of Vy respect to y is the magnitude of for V infinity, right, is delta naught divided by L naught cube. So it's a very, very small value. So definitely this is goes to 0. And for the last term here, second derivative of Vy respect to y, all right, so it's also a very small value. So that's why for the whole equation, all right, so the second equation here, then we will eliminate it from the analysis of the velocity profile for the velocity boundary layer. Okay, now then if that's the case, right, so now how can we estimate this value here, the value of delta naught over L naught? All right, so then it will then form from this part here, this section here, from the order of magnitude. So now this is the answer for the order of magnitude for the first equation of change of momentum for the x direction, right, that we have proved just now. All right, so then we'll equate, right, so we'll equate the order of magnitude on the left hand side, right, so which is V infinity squared L naught. All right, so and we equate it to the order of magnitude of the right hand side here. All right, so suppose this one, yeah, we are not checking anything on it, so assuming that the order of magnitude would be somewhat similar to this one because of the homogeneity of the equation, right? So and for this term here, viscosity divided by density, we can also express it as the kinematic viscosity, right? Okay, so but we will not reduce it yet, we will not simplify it yet. So it will then viscosity divided by density, and the order of magnitude for these two terms here, all right, so if you analyze, all right, so so just now we have compared, right, so what happens here, we have already proved the second derivative of Vx respect to x is much smaller than second derivative of Vx respect to y. Yep, right, so if you compare these two then, right, so Now, that's why when we do the analysis to find out what is the magnitude of delta naught to L naught, right? So instead of using this one, we are going to use this term here, right? So we are not going to use this term for the analysis, all right? So that's why we are multiplying this to V infinity and delta naught square for the analysis, all right? So let's say this is the order of magnitude, okay? So with this, let's say we rearrange the equation, right? So let's rearrange the equation step by step. So then we'll have delta naught square here divided by L naught equals to, let me see, equals to this one, viscosity divided by density. Then we will have, okay, density will still be here. And then we'll have V infinity, right? V infinity square and V infinity here. Anything else that I need to move? I think at the moment it's like this, right? Okay. Now, but this is square, right? So let's say we try to make it uh, more tiny so that it's more convenient to for the analysis. So let's say we divide both sides with L naught. Okay, let's divide both sides with L naught, right? Then you have delta naught square divided by L naught square, and you then have, so you simplify this as well, then you should have viscosity divided by density multiplied to V infinity and then multiplied to L naught, right? So but this is a square term, right? So then square root of it, then we will have equals to uh, this one, right? This one square root of viscosity divided by density, viscosity, and L naught, which if you look at this one, right, is an inverse of the Reynolds number, right? It's an inverse of it is the inverse of the Reynolds number. So therefore, right, so the ratio of delta naught to L naught, right, so we can express it as 1 over the square root of Reynolds number. Okay, so which means you can expect when the Reynolds number is very high, almost approach turbulent flow, then this fraction here is even smaller, and the thickness of your velocity boundary layer, it will actually get thinner and thinner, right? So when the Reynolds number is very high, which is written here. So from this equation, right, so you can suggest, it suggests that the boundary layer thickness is small compared to the dimension of the submerged object. So this one, it refers to the linear dimension L naught in high Reynolds number flow. Okay. Now, so this is the Navier-Stokes equation, right? Just now the Navier-Stokes equation for flow in y direction, right? So based on the order of magnitude analysis, all right. So just now I've go through with you all, right, because of all this fraction here. Since now you have an idea, your delta naught over L naught is 1 over square root of Reynolds number. So which means all this, it will be even smaller. So small that all this term here, you can assume it to be all this term, right? So it will approach 0, right? So yeah, we left with this term then. But this then, because it's equals to 0, right? So then it proves that the pressure gradient in y direction is a lot smaller than compared to the pressure gradient in the x direction, right? And so therefore, the whole equation 3 is cancelled. And then we have covered this just now when I go through this part here with you, right? So when we compare this one, the Navier-Stokes equation for flow in x direction, right? So why this term here we assume to 0? Because from order of magnitude, right? So this one is V infinity divided by L naught square, whereas this is V infinity divided by delta naught square. So it's this term here is the order of magnitude is much smaller. So therefore, you can also assume it to be negligible and discard it from the Navier-Stokes equation, right? So therefore, right, your boundary layer equation, right? So the Galois equation, it will then just reduce to this form only for two-dimensional flow, right? For fluid with constant viscosity and constant density, right? So this would be the Galois equation for the velocity boundary layer, which then only later we will apply it for further analysis to solve it, right? The next part of our lecture, then it would be how to solve this using the exact solution method. But we are not going to solve it completely. We are going to learn how to simplify it, because if you look at this equation, we have partial derivative of Vx respect to x, right? And also respect to y, All right, so it's a partial derivative. So how do we solve it? Okay, now before I proceed further, all right, so we better take a break. Now, at the moment, any questions so far? Anyone? Any questions so far? Are you still with me? Any questions so far? Still okay. All right. So this is still okay, right? About the order of magnitude. Okay. So the next part, it will involve some differentiation. Then you need to recall back some of the skills that you applied to solve differentiation, like the chain rule and the product rule. So that will be a little bit challenging. All right. Okay. So let's take 3 minutes break. All right. So we will come back at 11:25. All right. So come back at 11:25. Then we'll proceed with the second part and the last part of our today's lecture. Yeah. Okay. Oh yeah. So I'll post the camp codes in the chat area. Yeah. The camp code is in the chat area. Okay, so the campus code, it will still be valid for another 6 minutes plus, right? So remember to take your attendance, because I think there are another one, at least one student yet to take the attendance. Okay, now let's continue with this part here. So just now we have used the order of magnitude to prove, right, so how we reduce the boundary layer equation into just these two equations, right, the continuity equation that we still need to apply, and also this one, the Navier-Stokes equation, the x direction, right, so that we have already reduced it using order of magnitude method. Now then, how do we solve this equation then? Because it's a partial differential equation, right? Now, this solution here, the exact solution method, is proposed by Blasius. So in his proposal, one of the proposal is he's assumed that the pressure gradient here, it would be almost equals to zero. That's assuming that for the flat plate, right, because it's a flat plate, right, it's not a curvature, right, then we are assuming that suppose the pressure at the front part and towards the end of the object, it would be the same. So in that case, then the pressure, the change in the pressure in the x direction, it would then be negligible. So that's why it's assumed to be zero. Now then, to further, so then which means, right, this equation here, the downward equation, this part here, it will be equals to zero, right? But then we still have the Vx, right? It still changes in the x and y direction. You have partial differential equation. Now then, he proposed few things here. One thing, he proposed a stream function. Okay, you can look at this slide here, right? So he proposed a stream function such that Vx, it can be expressed as the first partial derivative of the stream function with respect to a y direction, right? And to solve it further, then he also proposed, they call it the non-dimensional equation, which is, you can call this as eta, right? The name of this Greek symbol here is eta, all right? And then it's equals to y multiplied to a square root of v infinity divided by kinematic viscosity and x. So this here is the kinematic viscosity, right? Kinematic viscosity. Okay, so you'll be seeing a lot of this term from now onwards. Kinematic viscosity, which is equals to the viscosity divided by the density. Now, why is it this term here that he used to do the as the non-dimensional equation so that he can solve the two governing equation for the boundary layer, right? And so it's actually just a guess value, right? He had tried with so this person here, Blasius, he has tried with a lot of parameters and he end up, right? So with the dimensionless number that he tried to solve the two equations just now, he had run through several ones and then he solved everything, right? So eventually, when he compared the solution, this one is the guess value that gives the tidiest solution or the most simplified solution. So that's why this is now being learned by everyone when we talk about the boundary layer, right? And then what's the relationship between this eta here and the stream function? So it's called psi for this great number, right? So where the function of eta, all right, is equals to the stream function divided by square root of this is the kinematic viscosity multiplied to x and v infinity. So which means if you rearrange this, the stream function, it will be equals to square root of v. I'll just say vx v infinity. Yeah, it'll be faster. Square root of vx v infinity multiplied to the function of eta. All right. So these are the three important things that he proposed. All right. So now, how do we simplify it? All right. So the first thing what we do last time, right, when we deal with the equation of continuity, what we'll do is we'll first simplify it, right? So where we know that there's no flow in the y and z direction, then the dvy dy and dz equals to 0, then which means then this will also be equals to 0. Now, then if let's say we use a stream function, you can actually prove it. Eventually, the sum of this is equals to 0. Okay. But what I'm going to do now onwards, right? So you notice that I'm going to discuss both your tutorial question and all this solution here at the same time, because the answer is the same. All right, so I better not waste the time, right? So we combine it so that I can go at a more suitable pace, right, thoroughly for each one. Now, so let's look at the first question here. So Blasius' laminar boundary layer solution, right, is an excellent example of the use of stream function to simplify and solve the partial differential equation of the fluid mechanics. So to solve these two, it actually refers to the equation of continuity and also the Navier-Stokes equation for flow in x direction that we have simplified flow in x direction. Right, so he substitute Vx and Vy from the equation. Now you need to show that, right? So eventually, all right, so the two equation, these two equation here, it can just simplify into this form here, or in terms of a stream function. All right, so then which means what we'll need to do at the first step, right, is actually to prove, okay, this part here, it will be equals to 0. Okay, so I'll discuss based on here. So it's the same for both sides actually, right? So let's see. So you see, drop out equation 1, and then he'll need to introduce the stream function into this Navier-Stokes equation for flow in x direction, right? So to convert it into this form. So how we actually do it? So it's by introducing the eta, this one, the eta here, and the stream function. Okay, let's look at here. All right. So now if Vx, right, if Vx is equals to the first derivative of the stream function with respect to y, right, so we'll try to substitute it here. Okay, so from the equation of continuity, right, first derivative of Vx with respect to x plus first derivative of Vy with respect to y is equals to 0, right? So we can also rearrange it further, right? So then to express it in this form, okay, then now let's say we start to substitute the stream function. So we are taking partial derivative of Vx, all right, which is expressed in this form here. So Vx, when expressed in stream function, is the first partial derivative of stream function respect to y, right? So it's expressed in this form here, right? So which means your first partial derivative of Vx respect to x now is transformed into this form here, all right? So okay, let me highlight it. So this part, the Vx is this one, all right? So then is equal to the first partial derivative of Vy respect to y, the negative partial derivative of it. Okay, now let's say we want to try to get an expression for Vy, right? We'll try to get an expression for Vy, right? So what we'll do then, we'll integrate, right? Integrate both sides, right? So integrate both sides by with respect, it should be with respect to y. All right, so if you integrate both sides with respect to y, so then which means negative Vy, it will then be equals to so integrating with respect to y, then it will be first partial derivative of the stream function with respect to x, right? Okay, so then rearrange further, which means Vy is equals to first partial derivative of stream function with respect to negative. That will be a negative form. So you have yeah, equal to negative of first partial derivative of stream function with respect to x. Okay, so then if now if you substitute back, right, into this equation, let's say if we do it again, right, then it will actually prove that it's equals to 0. Okay, so I'll just continue from here. So just now, right? Okay, so now plus first partial derivative of Vy, so it's negative. So for Vy is negative first partial derivative of stream function with respect to x, right? So and then you need to take partial derivative of this respect to y, so equals to 0. So if you rewrite this, what you see is second derivative of stream function with respect to x and y minus the second derivative of stream function with respect to x and y as well. So from here, yep, you have proved that yes, is equals to 0, and therefore equation of continuity can be discarded. Okay, so this is how you can prove it. All right. So if you want to, you can do a quick screenshot for this solution here. The session is also recorded. So for this week, I'll be uploading the link for this the actual lecture session that we have. Previously, I couldn't do it because the link, right, for meeting, for Teams meeting is only available for 2 months, right? But for today, it's like 1st of July, right? So it will last until end of August. So I think it's still available until during your exam period. Okay, now so this is how we can prove that the equation of on continuity, everything is equal to 0, and we can discard it. So the next thing is, all right, so how can we now express your equation, this one Navier-Stokes equation here, this Navier-Stokes equation in x direction that we have already simplified in stream function, so that, all right, so you need to use stream function, so that you using stream function here, so that you can convert, all right, you can convert this partial differential equation and have it later, eventually, right? There are still a lot of steps. Eventually, when you solve everything, it will then turn into an ordinary differential equation, right? So let's go to the second step here, where you see how we are going to express all this in, in this one, in stream function. Okay, so now, which is the same as what's the request here that you're asked to do, right? You need to show that eventually by using the stream function, it will lead to this answer here. Okay, so now, all right, so this is the equation of continuity, right? So never stop equation. And just now we're assuming that the pressure gradient, it would be 0 since it's a flat surface, right? There will be no change in the pressure gradient. Now, so we have already at this one, your Vx, right? Okay, so okay, perhaps let me rewrite also so that you can compare. Vx so I'll be rewriting your viscosity divided by the density as the kinematic viscosity. All right, so now we are going to express all these terms in terms of the stream function. So for Vx, we know that is when expressed in stream function is first derivative of the psi respect to y, right? Then for this one, okay, now onwards, all right, so for dvx dx, all right, so which means you're taking partial derivative of this d psi, right, d stream function respect to y, right, and this respect to x, right? So then you have Vy, right, which just now you have solved it, is first partial derivative of stream function with respect to x. Okay, then for this term, it will be Vx is partial derivative for stream function with respect to y, right? So you need to take partial derivative of this with respect to y as well. Okay, so then for the last one, all right, so it's the second partial derivative of Vx respect to y. All right, so wow, this one. Okay, so so you can expect it would be something like this, because you know that Vx is the first partial derivative. Okay, let me write it first. All right, so you know that Vx is the first partial derivative of the stream function respect to y, right? Okay, so then when you simplify it, so it would then be equivalent to the third partial derivative of stream function respect to y, right? Just that's straightforward. Okay, then for the left hand side, okay, now let's tidy it up. All right, so it would be first partial derivative of stream function respect to y, right, multiplied to second partial derivative of stream function respect to x and y, all right, then minus partial derivative of stream function respect to x multiplied to second partial derivative of stream function respect to y. So this is how you finally obtain this expression here. Okay. All right. So everyone, are you still okay? Any question at this moment so far? Any questions so far, everyone? Oh, okay. Good, everyone can still follow. Okay, now let's try the next one. Yeah. So the next one will start to be a little bit more challenging. Okay, so now you have turned the equation into a stream function. Now, in case if you want to know, right, or if you really want to try out whether the eta, which is equal to this value here, whether it's a really non-dimensional number or not, right? So you can go through this slide here. They have already proved that yes, it's actually dimensionless. Okay, so what we'll need to do now, because if you look at this equation here, it's still a partial derivative. Your stream function here is all expressed in terms of respect to x and y, yet it's still a partial derivative. So we'll need to then now start to apply this eta value here to change it into, right? So here then is the part where you apply eta equals to y multiplied to square root of v infinity divided by vx, right? To turn it into an ordinary equation. So which means, right, so you can imagine now, each of this you need to do the partial derivative of stream function with respect to eta, right? So it's quite a lot of work. Okay, so now okay, the solution for both the tutorial question and here is the same, right? So I'll use the tutorial one, all right, so to guide you through the process here. So now it says we wish that the stream function to depend on the dimensionless group eta, but it cannot depend on eta alone. So the stream function has a dimension of actually meter square per time, right? And the eta is dimensionless. Therefore, it must depend not only on the eta but also on some other variables such as the x, y, the kinematic viscosity, and also the Vx. And they have found that such combination, it can, by Blasis, right, is expressed in this form, right? So after rearranging the stream function, right, so if you look at it, is expressed as this one, Vx V infinity multiplied to the function of the square root of it multiplied to the function of eta. So now they want you to prove it. So just now we have expressed Vx in terms of the stream function, right? They want you to find how it can be expressed in terms of eta. And same goes to the Vy, right? So just now you express in stream function, then eventually how we actually, so how we actually, then into the next step, you express it in terms of eta. So it's when you express it as a function of eta of first derivative of eta or second derivative of eta, then only the whole Navier-Stokes equation you will turn into an ordinary equation. Okay, so now let's try for Vx and Vy. So for Vx, all right, so just now we found that it's first derivative of stream function with respect to y, right? Okay, and your stream function, if you look at it, okay, so okay, let me shift it a little bit lower. Right, so the stream function is given by this expression here, which is kinematic viscosity multiplied x V infinity and the square root of all these three terms here multiplied to the function of eta. So which means if you look at the stream function, right, the stream function itself is a function of x, y, because your eta you have a y term, of v kinematic viscosity, v infinity, right, and also the function of eta itself. So it's a lot of things, right? So that's why if let's say Vx is equals to first derivative of stream function respect to y, so this stream function itself, right, because it's also a function of y, right? So which means then you need to apply the chain rule such that then it should be expressed in terms of the first derivative of the stream function with respect to eta multiplied to first partial derivative of eta with respect to y, right? So you need to apply chain rule, right? Because your stream function is also a function of y. Okay, so then now let's differentiate, all right, the stream function with respect to eta. So the eta in stream function, right, only appears here, which means you will be differentiating this one respect to eta only. So okay, then which means it will then reduce to, so square root of Vx V infinity multiplied to first derivative of function of eta. All right, so this should then be the answer for, okay, how should I write it for this one? Okay, for this first term here. Now then we also need to take partial derivative of eta respect to y, right? So for that, so eta is equals to y multiplied to square root of v infinity over vx. Okay, so if you take partial derivative of eta respect to y, which means it's just as simple as, let's see, it's just as simple as you're left with v square root of v infinity over vx. Okay, so now then we will substitute it back here, right? So multiply to v infinity over vx. All right, so which means if you simplify this, right? So vx, this vx here and vx here will be cancelled out, and then square root of v infinity multiplied to square root of v infinity. So which means it will then be equivalent to v infinity only, right? So then your vx, it will then equals to v infinity multiplied to first derivative of the function of eta, right? Or which means if you rearrange this, we can actually express the function, the first derivative of function of eta, right, is equals to Vx over V infinity, which this term here, it actually gives you the dimensionless velocity, right? It's actually the dimensionless velocity. Okay, all right. So is it okay so far? Any question, everyone? So if no, then I will proceed further. Yeah. All right. So the next thing is then we will need to solve for Vy. All right. So I'll need some space. Now for Vy, right? So for Vy just now, right? So we have found an expression. It will be negative of string function with respect to x. Now let's focus only on this part here to solve for the expression. Yeah. Okay, because this one is quite challenging. Now, for string function, first derivative of string function with respect to x, as mentioned, right, your string function is a function of x, y, the kinematic viscosity, and v infinity. And okay, let's look at the string function equation. So Vx, V infinity, and then multiplied to the function of eta. And don't forget here the function of eta, right? The eta is also y multiplied to V infinity over Vx. So, which means if you look at this term in the string function, right, you have x here, you have x in here as well, right? You have the variable x, which means if you are going to solve partial derivative of the string function with respect to x, then you need to use product rule, right? As if this section here, it will be your u x, and this section here, it will be the vx. So you need to apply the product rule then. Okay, so you need to apply the product rule. And if you recall back, right, so if let's say if it's the product rule, du v dx, for example, so it will be u multiplied to dv dx plus v multiplied to du dx. Okay, so this would be what I'm going to write now on this section here, this line. All right, so keeping u constant first, so you have v square root of vx v infinity, then we'll differentiate the function of eta with respect to x. So which means then it will be expressed as a partial derivative of function eta with respect to x. Okay, plus now we'll differentiate this expression here with respect to x. Oh, sorry. We'll retain it as constant, right? Okay, yeah, we retain it as constant. So here, function of eta. So then we'll need to find an expression to this one, right? We'll need to differentiate it. Okay, so let me solve it here on a separate part. All right, so if u is equals to okay, if u is equals to vx v infinity, all right, and okay, I'll put it as a square root, easier, square root of it. So, and I want to solve the partial derivative of u respect to x. So, which means then it will be equals to square root of v multiplied to v infinity, and then your x, it will then be, now it's half, right? So then differentiation is minus, so minus 1. And then don't forget to multiply it to the to this one for the coefficient. All right, so which means simplifying it, then we'll have negative, oh sorry, it's not negative half, it's just half. Okay, it should be just half. Right, so it will be half, and then okay, let me think, negative 3 over 2. Oh wait, yeah, I did some mistake, right? Okay, let me see, because here it should be, okay, this should be just half because it's square root, right? It's just half minus 1. All right, so then which means you have, okay, we this one, kinematic viscosity multiplied with v infinity, and then it's yeah, okay, yeah, x to the power of negative half. So which means if you rewrite it, right, so you have half square root of v multiplied to v infinity divided by x. Okay, so then I'll substitute it here. Okay, let me rewrite it. Okay, so it will be half multiplied to square root of v, this kinetic viscosity multiplied to v infinity divided by x, then multiplied to function of eta. All right, so this part here is your derivative of the u. All right, and same goes to this part. This is the derivative of the v. right? So this is u, this is v. Okay, now here comes this part here. Now if we look at this second line, square root of vx v infinity, this is partial derivative of eta respect to x, which if you recall back for eta, there's this eta here, it's also a function of x. All right, so then which means we will need to apply next part here, then the chain rule. Right, so applying the chain rule, so it's partial derivative of eta respect to eta first, then multiply to partial derivative of eta respect to x. All right, then continue with the rest. All right, so then on before we can write the second line, right? So you need to get the expression for this term here, this term, the derivative of eta with respect to x. Okay, now, all right. So for the derivative of eta respect to x, all right, where eta is equals to y multiplied to square root of v infinity over vx. Okay, so wow, all right, okay, this is let's see how we do it. All right, so then you assume the y multiplied to square root of v infinity over v here is still constant. All right, so then we'll need to differentiate this one, right? So for now, so which means it's x to the power of negative half, all right, and then minus 1 again, and then we'll also need to multiply to its coefficient, right? So then it's negative half, right? So then here, the next line, so the x part, it will then turn into something like negative half. Let's see. Yeah, suppose it would be x to the power of negative 3 over 2. Okay, but what I will do, I will try to write it in this form here so that you see how later we can actually combine it. So let's say if it's x to the power of negative half, then which means this term you can actually express it like this, right? 1 over the square root of x, and then multiply it to this one x to the power of negative 1, which means you can express it in this form, right? 1 over x, which if you simplify the whole thing, then your derivative of eta respect to x, right? So it will be, okay, let me rearrange it further. So it will be, it will look like this, negative half, right, of y multiplied to v infinity, right? And then, so this is also square root, right? So you can combine with this. So it will then be square root of v infinity over vx, right? And multiplied to 1 over x, okay? Which this whole thing here is equivalent to eta, right? Is equivalent to beta. So you can then simplify the whole expression for the partial derivative of eta with respect to x will then be equivalent to negative half of eta over x. Okay, so with this, all right, okay, okay, it's a bit messier. Let me see, where are we? Okay, it's a bit messy. Let me, okay, so let me separate it. All right, so let's continue with the solution here. So substituting it back, so it would then be square root of vx v infinity. So this first partial derivative for a function of eta with respect to eta, right? So you can simplify it and express it as this one, in this form, first partial derivative of function of eta. Then you can also now start to substitute, right? Substitute the negative half eta over x, okay? And then plus this one, okay, v infinity divided by x, x then function of eta. All right, so if, okay, let me see. Okay, so if you look at here, right, so you notice there's x here and there's x here, but this is the square root of x. This is divided by x. So we can actually simplify it further such that we will have, all right, so square root of v multiplied to v infinity then divided by x, right? Okay, then you have eta multiplied to the first derivative of function of eta, then again plus half of this, right? So v infinity x multiplied to function of eta. So the whole thing, if you simplify it, because you have similar term here, right? Okay, so then let's say we factor it out, right? Half multiplied to square root of v multiplied to v infinity over x. Okay, so then multiplied to a function of eta minus eta multiplied to the first derivative of function of eta, right? So then this is the solution for the partial derivative. So this is the solution for the partial derivative of stream function with respect to x. Okay, that's only the solution for stream partial derivative of stream function to respect to x. But don't forget we are actually solving for vy. All right, so which is equivalent to negative of the stream function, partial derivative of stream function with respect to x. So which means then applying the solution that we have found here, then which means negative half of square root of v multiplied to v infinity over x, then function of eta minus eta multiplied to first derivative of function of eta. Okay, all right. So for today, all right, so I think we only managed to solve out to this part here. So we have still a lot of term for the equation, right? Now, any questions so far for this section here first, for the Vy, how to express the Vy in terms of eta? Yeah, any questions so far? And has everyone taken the attendance just to check, right? Because you left with 3 minutes only. So two more minutes only. So in case if someone missed it, I'll post the passcode again in the chat area. All right. So remember to take your attendance. So I will stop here for today. So tomorrow we are going to continue. So we have only solved it up to finding the expression for Vx and also Vy up to this slide here, and also for the tutorial question. So for tomorrow, you are going to learn how to derive the expression for these three terms, and you are going to see how when we substitute it back to the Navier-Stokes equation, the second line, right, how it will reduce to this one, the ordinary differential equation. And from there, Brassers solve it using the power series solution, right? So he do the calculation, everything, right? Eventually, he come up with this profile here that we can conveniently use it to solve for any question regarding the velocity boundary layer. Right, so we'll continue tomorrow, right? And actually also to get the expression how to calculate the boundary layer thickness. Right, so we'll continue tomorrow for this section here, and also the momentum integral method. Right, so yeah, we'll go with the flow, right? Not to rush. So make sure everyone understand it. So yeah, all right. So so if you have time, you can also practice on the part on how to solve Vy. All right, practice about this one, the product rule and the chain rule. Give it a try. All right, okay. So the most challenging part is actually only the Vx and Vy part. So later, the solving the another three parameter is like you have the expression already, then we will just need to apply it only. Okay. So if everyone has taken your attendance and no further question, then that's all for our class today. Right. So we'll continue during the tutorial the tutorial session tomorrow. All right. So make sure you don't miss the class here. So as for the scope of the exam, all right. So in case if anyone missed it, I'll post it in my times really. All right. This announcement here is on next Thursday. Right. So we'll gather at 2 p.m. at this venue. Take note, it's closed book, right? So it's everything about the lecture and tutorial material that we have covered from week 1 to week 9. Please make sure you go through the lecture example as well, all right? Because your lecture example and tutorial example, we cover a lot of different geometry, right? So focus on the learning outcome number 3. You have one question for formulating the velocity profile and one question for temperature profile. And as mentioned, for the velocity profile, you definitely need to master the shell balance method, the shell momentum balance method. All right. So, but do not neglect the Navier-Stokes equation as well, because in case if you can't make it for this one, then this is your backup. All right. Okay. So as for thermal boundary layer, the thermal profile, right, the temperature profile, make sure you master both the shell balance method and also the equation of change for temperature. Right, so you can focus more on all these topics here. The rest, I can't say that you can ignore it, because some of the concepts you may still need to apply into the formulation of velocity or the temperature profile. All right, but you can go through it briefly and focus more on this two sections. Okay. So yep, that's all for today. I'm late for another class also. All right. So thank you very much. If you have any question, you can ask me tomorrow. Yeah. Okay. Thank you, everyone. Bye bye. Yeah. Have a good day, also, everyone.